Hello and welcome to Bruker Nanosurfaces Division webinar series. Today you're going to be hosted by Matt Novak and Adam Feinstein. We're going to talk to you about complete LED surface metrology capability for the line of products that we make in our facilities. And we appreciate you taking part in this webinar. So LED research and production require reliable measurements of many properties of the materials. There are substrate measurements that take place for the beginning of the process for roughness, defect, flatness, and bow of substrate wafers. There are substrate front-end measurements for features such as PSS, pattern sapphire substrate, where you're looking at height, pitch, and width of the features, or as well as sidewall angles. There are front-end process measurements for epi defects, pinholes, grain sizes, roughness, looking at electrical properties, film thicknesses, and chip and die step heights or electron rod heights. All of these things are subjects of intense metrology along the way through LED manufacturing process. And each of these properties needs control in all the way starting through research and QA/QC through production. And the key here that we'd like to focus on today is that there is no single measurement system that can measure every one of these properties efficiently. So Bruker offers a complementary suite of tools across various platforms to address these needs. We have tools in AFM, Stylus, and 3D optical microscopes that will provide a complete measurement solution. So here you see a picture of this complementary suite of metrology instruments, the Dimension Edge AFM, the Contour GT 3D optical microscope, and then the DECTAC XT Stylus profiler. These are listed in terms of methods for process development and QA/QC. The AFM tools can measure Nano-Scale features at incredibly high lateral resolution as well as vertical resolution. The 3D optical microscopes can do rapid non-contact measurements for roughness, PSS height and width. Some step height measurements can be done as well as many other applications. And then Stylus profilers can provide excellent capability for wafer bow, flatness, ITO thickness, and step heights. And the key to take away from this presentation material is that these tools really are a complementary set of tools that can span across entry into the process development, where an AFM would be critical, all the way through to production monitoring at higher speeds and at greater volume, where the more automated staging capability of the 3D optical microscope might be of use. So we'll go through in terms of larger to smaller scales, and so this slide is a representative of what the Stylus systems can do for quantifying larger scales. For example, wafer bow, where you're making a scan across 150 millimeters on a wafer. The DECTAC Stylus system can provide rapid and accurate trace measurements for this bow characterization, as well as a unique software capability to compute stress in coated wafers. You can see these plots on the bottom are representative of the curvature change for wafer bow, and then as well the 2D stress plot here on the right-hand side. The 3D optical microscopes can quantify roughness over a large field of view, but at the nanometer level for accuracy. The Contour GT optical microscope can provide sub-nanometer vertical resolution over large fields of view, such as you see on the left-hand side of this panel. And stitch measurements can quantify wafer shape as well, such as you see on the right-hand side of this measurement panel. So this is a good way to look at quantifying material properties and measurement parameters at the micro scale. And with that, I think we're going to move down to discussion of doing measurements at the nanoscale. I'll hand it over to Adam Feinstein.
Hi, this is Adam Feinstein speaking. As Matt has been describing, the Bruker metrology solutions cover the nanoscale out to the micron scale, ranging from process development to production requirements. The AFM is the resolution leader in the product line, demonstrating the capabilities at the nanoscale. Here we have nanoscale features demonstrating the ability of the AFM to measure things like roughness and defects at the nanometer scale. So we have the dimension icon and the dimension edge AFMs, which can identify sub-nanometer changes in surface topography in Z. This is demonstrated in the images on the left-hand side, where we show roughness effects of sub-angstrom level on the far left and around 1.2 angstroms on the right. These effects are critical in process development, especially as bare wafer substrate, pattern sapphire substrate, and epitaxial layers are investigated. Additionally, low-level defect characterization of less than 5 nanometers in diameter can be demonstrated and resolved using the AFM. One critical application for the AFM is pattern sapphire substrates. Pattern sapphire substrates are increasingly being used by LED manufacturers for efficiency improvements. What the PSS does is it decreases the total internal reflection of the device, allowing for higher efficiency. It also reduces layer mismatch effects that lower quantum efficiency. There are different size and shapes ranging from greater than 5 microns to less than 2 microns, and depending on the pitch, shape, and size, Bruker has a solution ranging from AFM to 3D optical microscope. And these can be combined for process development, QA, QC, all the way through automated production. The parameters of importance for the pattern sapphire substrate are the height, diameter, pitch, sidewall angle and 3D profile, as well as the shape uniformity. The dimension edge with AutoMET is the specifically designed AFM for pattern sapphire substrate measurements. It's a semi-automated metrology system which allows automated measurement of up to 9 wafers as well as automated data analysis. This automatic measurement and analysis and reporting allows for simple operator use. In addition to the pass-fail criteria, which removes the need for advanced technical training at the technician level. Tip calibration is also built in order to reference system to system. The Dimension Edge PSS with AutoMET provides resolution well beyond traditional optical techniques, as we've shown down to the nanometer scale. It also has additional capabilities to measure roughness, monitor epitaxial process, and image defects that are needed for early process and R&D learning. AFMs have the unique capability to measure the full 3D profile of the PSS structure. As you can see here, we're able to resolve the differences in sidewall angle ranging from 45 degrees at one part of the feature to 70 degrees for another part of the feature. Even very small PSS structures can be resolved. In this case, we're showing the 3D profile of the PSS structure with a pitch of around 3 microns, but a spacing between features of less than half a micron. So the AFM is clearly demonstrating the resolution capability that's needed for advanced structures. While we're showing the ability to do metrology, the AFM is also able to provide information regarding defects. Here, as part of an ongoing process QA/QC role, the AFM is able to demonstrate defects specific to the pattern. These defects persisted through multiple wafers and across multiple tips, so we were able to confidently know that the defects were real. The Dimension Edge PSS with AutoMET is optimized for automated results, has a simplified operator user interface and a logical AFM workflow, automatic report generation in both short and long format, automated measurement across multiple wafers with automated data analysis, and a simple pass-fail criteria which the engineer or supervisor can set. All this equates to a AFM suitable for entry into process development through QA/QC and into production.
So as Adam has been describing the unique capabilities of the AFM to span across process development and through to production for the Dimension Edge tool, we have concurrently developed a 3D optical microscope solution for this space, which is capable of interfacing with wafer handling and to provide a higher speed, higher throughput type metrology once the process is fully fleshed out and the pattern sapphire substrate material is known well and has been characterized. We offer then a fully automated operator-independent measurement solution in the Contour GT-X8. This is a vibrationally stable design that's geared specifically for production environments with self-calibrating or continuous calibrating optics for the most accurate results, capable of handling up to from 2 to 8 inch sapphire substrates to be measured on one tool. And this is a fast solution where you can measure. Here on the lower right you see a simple automation setup screen where you have 13 sites, and these are capable of being measured in under 2 minutes for one wafer. And the key here is to take advantage of this process development through to QA/QC and production, this link between the correlation from what the AFM provides at high resolution to the metrology solution for the 3D optical microscope, and you can make good close correlation for the patterns that have been developed for your process, and then take advantage of the speed of the Contour GT 3D optical microscope for process control and process monitoring after that has been done. And here you can see on the top some structures that were measured using AFM, and then the same structures measured on the Contour GT, and you have very close results, but this takes about 5 seconds to measure. And the Contour can accurately measure height, pitch, width, and defects on a larger scale. So this is where the complementary nature of these two measurement platforms comes into play. The Contour GT-X8 will provide the most stable PSS production measurements over time for areas where the pitch is within the diffraction resolution of the optical microscope. You can see here for long-term repeatability on height, width, and pitch, you have 3 sigmas for height on the order of 5 nanometers, widths on the order of 17 nanometers, and pitch on the order of 2.8 nanometers, showing results over 5 days with excellent repeatability for these types of structures. And as I spoke about just previously, and complement to what Adam has described for the low, fine detailed and high lateral resolution of the AFM, the optical microscope can measure large fields, relatively large fields of view, and quantify or pick out defects that can be scanned in terms of automated software finding diameters, height variations, locations, or volume, and pass-failing these types of criteria based on errors in the process. So you can see on the left-hand side some pictures of incomplete structure or grossly distorted structure on both the left-hand, right-hand side. And these types of things can be seen easily with the optical microscope, which is a complement to the smaller scale detailed structures of defects that Adam was pointing out previously. And with that, we'll go back over to Adam to describe some of the more further capabilities of the AFM tools.
Beyond just resolution for pattern sapphire substrate, the AFM is a critical early learning tool for R&D. Things like magnesium doping effects on electrical properties can be resolved. gallium nitride surface parameters for dislocation, defects, stacking faults can be observed, as well as looking at the overall defectivity resulting from different indium gallium nitride ratios. These sort of things can really only be resolved with the AFM and are critical to improving the overall performance of the process and the end device. As we've been describing, the AFM can provide excellent resolution for resolving process attributes. Here, we're demonstrating island coalescence as part of the MOCVD process. And now back to Matt to describe roughness.
So Adam has alluded to the excellent capability of the AFM to measure epi roughness, but this is something that we've internally realized that sometimes the feature sizes are becoming larger and larger, but the roughness is at a low sub-nanometer kind of, or around a few handful of nanometers roughness. In which case, the real easier way to make this measurement and the more efficient way to make the measurement is over a larger field of view. And so here we take advantage of the sub-nanometer resolution of the optical microscope, the 3D optical microscope like the Contour GT, but looking at a millimeter scale laterally, all in one field of view. And you can get these types of data that are shown here. On the left-hand side, you have a 1.2 by roughly 0.9 millimeter field of view, where you have features that are on the order of 50 microns. And what you're doing is you're characterizing the roughness here in a way that gets you down to the few handful or less than 10 nanometers roughness and even down into the nanometer level of roughness, but you're doing it quickly and you're able to then characterize quickly process changes that might affect these features, which then correlate and change characteristics of the LED emission. Additionally, we also offer for 3D trace measurements and single trace measurements for layer thickness and steps down to the nanometer scale. Here, the DECTAC XT is an excellent system choice for providing highest accuracy for step determination. On the right-hand side, you see a 2.5 nanometer step measured to show variation in nanoscale topography and topology. Step heights down to 2 nanometers can be measured in this way, up to 500 microns. Multiple layers can be characterized if transition zones are accessible with the Stylus tip. So again, this is a comprehensive picture of a complementary suite of metrology tools offered by Bruker Nanosurface Division, ranging from resolutions at the nanometer scale and below, the nanoscale features such as defects, electrical properties, very small structured PSS, and high sidewall angle PSS. And for process development, QA, QC, and some production, the AFM is a key instrument for those issues and those applications. Then moving into more rapid non-contact measurements with the 3D optical microscopes, looking at epi roughness over larger fields of view, micron size defects and steps, as well as PSS heights, widths, and pitches at a higher speed for production inspection down to around the 2 micron times 2 micron scale, and pitches that are in that range can be done with the optical instruments. And then the Stylus profilers provide excellent capability for the larger waviness structure for substrates, wafer bow, flatness, and stress for all stages of production, as well as ITO thickness and step heights.
Here we're reviewing a table that shows the ability of Bruker's product line to cover all of your measurement needs, from front-end substrate measurements through the measurements required transitioning from substrate to LED manufacturer to LED manufacturer front-end process requirements. the multiple characterization parameters can be measured using our different systems through process development, QA/QC, and into the production metrology solution. As can be seen here, the solutions range from the Dimension Edge PSS to the Contour GT 3D optical microscope line, as well as the DECTEC XT surface profilers. Regardless of your measurement, Bruker has a solution for your product. And with that, this was Adam Feinstein thanking you for your attention. If you have any questions, my contact information here, please feel free to email me.
And as well, this is Matt Novak. I'm Applications Manager for the Stylus and Optical Metrology instruments. Please email with any questions regarding this presentation. We'll be happy to help. Thank you for your time.